So it's already 7:02, so we'll start. So as you know, this is a course on welding of advanced high strength steel of automotive applications, and we have already covered 2 live sessions on this course, and this is the third week live session which is going to be held now, and the date is 9th of September 2022. So before that, let me share my screen and kindly confirm if it is visible to all of you. So yeah, so this is the third week. So far what we have covered is we have studied about the different categories of advanced high strength steels based on the generation. The development has happened, and then in that we mostly focused on dual phase steels, trip steels, like what are their compositions, what are the microstructure, and how we get that those microstructures. And yeah, suppose with that same microstructure you are going to make a car body or a component, then and you are using a welding process, so how you'll be going to retain the same microstructure or a better microstructure, so that your weld is having a superior or at least a comparable property with that of base metal. So we saw detail about dual phase steels, and then trip steels, and then steels like hot stamping steels, and after that we went to the welding processes. So what are the welding processes that we can use for welding those kind of steels? So in that we saw that mainly there are three types of welding processes. The first one and the mostly used one is spot welding or resistance spot welding, and the second one the resistance spot welding we covered in the last week live sessions itself. And this week we will be going to learn about the laser beam welding. So the application of laser beam welding in automotive field. And then we'll also look about the conventional welding process, that is GMAW, and mostly advanced GMAW, that will be helpful for welding automotive components. So up to here, like in past 2 sessions, what I used to do is I used to summarize the content which was uploaded on the Swayam, and then the practice questions we used to solve. But this week what we will be doing is, first we'll see the problem, and through the problem we'll try to understand the concept, and then we'll answer the problem. So so whatever question I'm going to show you, try to solve that, and then we'll try to have the background of the keywords which will be involved in that problem, and then we'll try to answer it. So don't hesitate whether it's correct or not correct. Just tell what you think about that problem, and even if you get wrong, then it's fine. We're here to learn. We are here to learn. So yeah, so we'll start with the question number 1 of this live session. So the question is on your screen. You can read the question number 1 here. So yeah, the question 1 is which one of the following controls the stability of keyhole during laser welding of galvanized steels in overlap configuration? So there are different types of forces mentioned in the options. Just go through them and then try to answer. You can unmute yourself and tell the answers, or you can type in the chat box. Both are fine. So just read this question number 1 and tell your answer. Then we'll try to learn about the concept behind that. So here it is asking if you are welding a galvanized steels in overlap configuration. So what is overlap configuration? So let's say this is one sheet, and this one is another sheet. So one is overlapped by the other. So this is how an overlap configuration looks like. So now here you are going to make a laser weld. So in this configuration you have a steel which is galvanized, that is zinc coated, right? Galvanized means zinc coated steel. So in that case, what will be the controlling factor in the stability of keyhole? So yeah, Mohan Kumar has commented. Before solving this problem, first we'll try to understand what are the factors or forces or pressure which will be generating if you are going for a laser beam welding. So for that I have a slide for you. So here on the left side of my screen you can see the forces involved in laser beam welding. So what are the forces which are involved in laser beam welding? So there are basically 5 forces. You can see here on my screen. The first one is beam pressure. We denote it by PB. Second one is vapor jet force. Third one is recoil pressure. And fourth one is gravitational force. And the last one is surface tension force. So out of these forces, there are few forces which will assist the opening of keyhole. In laser beam welding, there are basically modes of welding, and one of the mode is like keyhole, and the other one is conduction. So these two are modes in which you do the welding. So if you are doing let's say if you want to have a keyhole generated in your workpiece, then the forces, some forces will assist you to generate the keyhole, and some forces will resist or assist in closing the keyhole. So here out of these 5 forces, upper 3 that is beam pressure, vapor jet forces and recoil pressures. So what do you think, like whether they are going to assist in opening or resist in opening?
Assist.
Correct. So basically they will help to make the keyhole, that is assist in forming the keyhole. Similarly, last 2 forces, that is gravitational and surface tension forces, these 2 forces will try to close the keyhole. So they will basically resist in keyhole opening, or they will try to close the keyhole. So here you can see like how these forces are generating. So let's say beam pressure. Beam pressure is nothing but the laser beam which is trying to penetrate inside your material. Vapor jet forces and recoil pressures. So vapor jet forces are nothing but if your material is since the temperature generated here is very high. So what will happen? Your material will melt in the liquid state, as well as if the difference between the melting point and vaporization point is less, then at that case what will happen? Sandeep, can you please unmute yourself? Yeah, thank you. So if your material is volatile, then what will happen? Vapors will also form. So material, if it consists low vaporization point elements like zinc or in some cases aluminum. So in those elements, what happens? The difference between melting point and vaporization point is very less. So just after melting, if you give more and more energy, they will start vaporizing, and that vapor will create a vapor jet forces. So we call it PV. And then from the Newton third law, as you know, same as if you see a rocket jet, so what will happen? From the exhaust size, exhaust will be coming out and it will create a thrust. So in similar manner, when this vapor will be escaping out from your cavity, so it will generate a pressure called recoil pressure, and that recoil pressure will also be assisting in the opening of this keyhole. So these 3 were the forces which are helpful or governing into the formation of keyhole. Coming to the forces which are resisting, that this is nothing but the gravitational forces. So here you have a liquid mass, and that liquid mass, on that liquid mass the gravity will try to pull down. So it will merge towards downward, which will basically resist in keyhole opening. And the last one is surface tension force. So here as we have a liquid here, so on the liquid surface the tension force will be there, which will also be resisting in the keyhole opening. So these were the basically forces which is basically acting in laser beam welding. So now coming to our question, which one of the following controls the stability of keyhole during laser welding in galvanized steel in overlap configuration? So as we know that in galvanized steel we have a zinc coating, and once you put the high energy beam of laser, so what will happen, this zinc will vaporize, and the amount of zinc vapor which will be generating based on the percentage of zinc you have on the surface or the thickness of zinc coating will determine the keyhole stability. So in the lecture itself, sir has demonstrated 3 cases. Let's say we have a pure steel without galvanizing, only steel. In second case, we have a steel with a coating thickness, let's say 1 micron. In third case, we have steel with coating thickness of 7 micron. So these 3 were the cases. So in that case, as here no zinc is available, here some amount of zinc coating is there, like it's 1 micron coating, and the third case is 7 micron coating. So in that, zinc amount will be varying, and this zinc vapor will determine the stability of this keyhole, right? So it's very, very important and a governing factor if you are welding a galvanized steel. So the right answer for this problem is vapor pressure. So Mohan, as you told, this is the right one, and the right answer is vapor pressure. So I hope you might have got the idea, like how this vapor pressure is governing in case of galvanized steel. Hello? Is it clear?
Yes, sir.
Yeah. So now now we'll try to solve the question number 2, which is droplet detachment in consumable electrode welding is always opposed by. So here in the last problem we talked about high energy beam process, that is laser beam welding. Here it is asking about a consumable electrode welding process. So in that case, if metal transfer is happening, so what are the forces which will be opposing the metal transfer? So you can see here the options and try to answer them.
Sir, I think surface tension.
Okay. Sandeep, you
Yes, sir.
Okay, fine. Surface tension. What about gravity, vapor jet force, plasma jet force? What they will do? They will assist.
Sir, gravity, I think gravity will assist the detachment of consumable electrodes, and surface tension will restrict the consumability of electrode.
Okay.
Yes.
Okay. And what about this plasma jet? What do you think? Plasma jet, will it resist or assist?
Maybe, sir, I'm not sure. In plasma, it will assist or oppose.
Okay. So now we'll before answering, we'll just understand what are the basic forces that will be acting in the consumable electrode welding process, and then we'll come back to this problem, right? So yeah. Now coming to the forces involved in metal transfer, like in consumable welding process. So basically there are 5 forces here also. You can see on my screen that there are gravitational force, aerodynamic drag force, electromagnetic force or Lorentz force, we also call it, and then vapor jet force and the surface tension force. So all these forces are schematically shown in this figure. So you can see this is our filler cross section. So this is our filler wire, let's say filler wire, and we are supplying enough current so that it can form a metal droplet. So this is nothing but a metal droplet. Now as this metal droplet is forming, you can see there are all these 5 forces are going to act. So, and the direction of forces are indicated here. So as you can see, first of all, if you are doing a downhand welding, that is your base plate is on the ground and your hand is above that base plate. So in that case, what will happen? The gravity will be acting opposite to the direction of your filler, and then it will assist the detachment of this droplet. So this gravity force will, due to gravity and mass effect, this drop will try to pull downwards, and it will try to fall downward. But what will happen if you are doing uphand welding? That is, your plate is let's say you are welding a roof which is above your head, and in that case you want to transfer metal droplets against the gravity. So in that case, what do you think? Gravity will assist or resist? Let's say
Gravity will assist, sir.
This is
come on,
Yes, sir.
assist
Sir,
or
gravity
resist?
force will assist.
I'm again repeating my question, that you are welding, let's say some 2 plates are there above you, let's say roof welding. So in that case, your hand will be below that plate, right? So gravity will be acting towards down, but you want to transfer the metal above you. So in that case, gravity will resist, na?
Yes, sir. Yes, sir.
Yeah. So depending on the welding position, whether it's downhand or you are doing uphand. So in that case, this gravity will be because gravity will be acting in this direction, right? But let's say you want to join this plate from bottom side here. From here you want to do the welding. So in that case, the gravity is acting downward, and you want to transfer the metal from below to the top one. So in that case, gravity will resist. So that also we have to check. So we should not say that the gravity will always assist. So yeah. So this was about the gravity. Now coming to the surface tension. So surface tension, as you can see, this is our surface of the metal droplets. So surface tension direction is in this way. Let's say here it is like acting like this, here it is acting like this, mostly tangential to this. So it will try to contain the droplets, means it will basically resist. It will resist the detachment. So the surface tension here is will be let's say negative or resisting. Coming to this vapor jet forces, so from this from where this vapor is coming, so it's nothing but from our base metal itself. So if some amount of your base metal is vaporizing, then vapor will be forming like this, and this vapor will try to push your droplet upward. So in that case, vapor force will also be resisting your metal droplet detachment. So it will be negative. Coming to the just a minute. Yeah, coming to this electromagnetic force and this drag force, or we also call it aerodynamic force. So these two forces will be acting towards these directions. And this is how the direction of the forces is there in the case of consumable welding processes. So I hope it is clear. So if you try to write down the forces in forces balance, so you can write it Fg, that is gravitational force, plus Fd, that is aerodynamic force, plus Fem, that is electromagnetic force, is equal to Fv, that is vapor force, plus surface tension force. So I am assuming, for writing this, I am assuming that I am doing downhill welding. That is, our electrode is coming this way and the base plate is in the bottom side, like below the electrode. So these three forces will be assisting, and these two forces will be resisting. So I hope it is clear.
Sir, aerodynamic drag, please explain about aerodynamic drag.
Huh. So this aerodynamic drag force is nothing but you have this arc, right? So this is a kind of let's say it is a shielding gas GMAW, gas metal arc welding process. So in that you will be having gases here, right? And the arc will be coming in this way. So let's say this is our electrode, and this is how the arc will be generating. So the arc flow will be like this, and this flow, let's say here you have a metal droplet, so this flow will try to detach this bubble. It's nothing but you might have used that soap bubble in your during your childhood. You might have used a soap bubble and you have blown it through your mouth, and that bubble came out from that toy. Have you done that?
Yeah, sir.
Yeah. So that air which you are blowing from your mouth is nothing but the aerodynamic drag force. So here in the welding, that air which you are generating, that analogy is whatever air you are putting inside that is same as in the welding. It is aerodynamic drag force. So it will be basically assisting to detach the bubble. Similarly, electromagnetic force. So in that arc column, we have electrons, ions, right? So electron will be there, ions will be there, and their number density will be very, very high. So between the electrons, electron, that repulsion will be there. Like light charges will be repelling to each other, and like charges will be repelling to each other, and unlike charges will be attracting to each other. So those forces, let's say we have unlike like charges accumulated at a certain place, so they will try to repel in this fashion, as you can see here. So they will try to repel, and then that repulsion will be assisting in detaching the bubble. So this is how these forces are helping or resisting in the droplet detachment. So is it clear?
Yes, sir. Please continue.
Yeah. So now we'll go back to our question. Droplet detachment in consumable electrode welding is opposed by. So as you said, surface tension, that is true. But in some cases, as I told, if you are doing uphand welding, so gravity can also resist or oppose your droplet detachment, right? So the right answer 1 and 2. If you are doing
Vapor pressure, vapor jet also will oppose, right?
yeah, correct. So this will also droplet detachment in consumable electron welding is always opposed by. So vapor will be coming from the bottom side, right, like this, and your droplet is here, so it will basically oppose the detachment. So vapor, surface tension, and gravity if uphand welding, right? But if you are doing a downhand welding, then only these two will be the right answer. Correct? Now we'll move
Yes,
to,
sir.
we'll move to next question. You can read the question number 3 on your screen. When the welding current is increased above spray transition current in GMAW, then what will happen? So first of all, you should first know that what is mean by spray transition current and what is the role of spray transition current in GMAW. And then how they are related to type of droplets, whether it's spray, short circuit, spatter.
Drop spray transfer occurs.
Who said this? Mohan?
Mohan.
Yeah. So yeah, we'll see the concept behind that and then we'll answer that. So you can see the graph on my left screen. So here it is plotted between current versus drop volume or in other case it is transfer frequency. So let's say this is our electrode and we are supplying some current, and the molten droplet is going to form like this. So this current. So as you increase the current, what will happen? The amount of, or the size of the size of this droplet will keep on growing like that, as you can see. Yeah. So but when it start, it will have a very small dia, and one moment will come when the dia of droplet, that is dia of droplet, will be equal to dia of your filler wire. So at a particular current value, this situation will arise, and that current we call it as a spray transition current, right?
Correct.
Yeah. So if you see the mode of metal transfer, so basically it start with the globular, at a low current, very low current. If you have a very low current passing through your filler, then in order to detach it, the size of droplet should be very big so that gravity can pull down into the pool. So at a lower current, the metal transfer mode will be globular. Now as you move, or as you increase the current further, so the globular to repelled globular, globular mode will be coming. So in globular, your droplet size will be very big so that gravity can pull it inside the whirlpool. In repelled globular, what will happen? You increase the current more than that of globular. So what will happen? So in that case, this droplet will grow, but the vapor is also coming. More and more droplet, as the droplet grows, vapor is also coming, and this vapor will distort the shape of this droplet. So vapor is coming from bottom side, and this globules is now converted into repelled globular. So the shape of this droplet is like a shoe or buffoon of a joker shoe. So it will look like this. Now if you further increase the current, so in that case, what will happen? The metal transfer mode will be converting into spray mode. So there the other forces, that is plasma jet forces, and those forces which are assisting the metal transfer will be, or Lorentz forces, they will be very high, and you will be getting spray mode, right? Very small droplets getting transfer, and that we can control like one pulse per droplets, like that we'll see in next slide. So here it is spray mode, and then if you further increase the current, then it will be going into jetting spray. So this is how if you increase the current, the metal transfer mode will be changing from globular to repelled globular to spray mode to jetting spray mode. So here it is least current in globular mode, here it is highest current in jetting spray. So this is how the metal transfer takes place. So coming to this graph, so here you can see current is increasing, the droplet volume is decreasing. Here you can see because let's say you are transferring from globular to spray mode, so here it is only one droplet, but here you can see this size of this droplet is went down, and it has broken into small droplets. So by increasing the current, the droplet volume will decrease, but the transfer frequency, you can see here it is one droplet only, but for the same amount of time we can transfer 4 droplets, let's say. So the transfer frequency is basically increasing. So the one moment will come when you have a balance between this droplet volume and transfer frequency at this particular current, where it will be equal for a given current, and there you can achieve a good mode of metal transfer. Now we'll go back to our problem. So when the welding current is increased above a spray transition current, so as I told, at spray transition current, the transformation from globular. So here let's say it is globular mode towards the left side, and right side let's say it is spray mode. So at the spray transition current, from globular to spray mode, transition will be taking place. So if your current is above the spray transition current, then obviously the transfer mode will be spray mode or drop spray transfer. So the right answer is option B, which is drop spray transfer occurs. I hope it is clear. Sandeep and Mohan.
Yes, sir.
Yeah. So now we'll move to question number 4. In pulse GMAW, just read these options and then we'll try to learn about them. In pulse GMAW, drop transfer is promoted, heat input is increased, in current is increased, jetting spray occurs. So what are the phenomena that is going to happen? You have to tell. Okay, Mohan is telling that mean current is increased. Okay, so we'll see what is pulse GMAW and then we'll come back to the answer. So here, let me erase this. So in pulse GMAW, instead of using a constant current type of waveform, what we use a kind of pulsing. So here it is a square shape or a rectangle, you can say, pulse, which we are using. So here there are few important parameters which are involved. So this side it is current on y-axis, and on x-axis it is time. So you can see there are basically two types of current involved here. Current which correspond to this minimum current, and we call it as a background current, denoted by IB. So background current, and the time for which we supply this background current is known as TB, or time duration for which this IB is supplied. Similarly, other current involved here is this peak current, that maximum current, and we call it as a IP, right? That is peak current, and the duration for which this peak current is supplied is called TP, right, or pulsing time. So this is the duration of TP, and this is the duration of TB, right? So there are basically four important parameters: IP, IB, TP, TB, right? So if you try to calculate the mean current, so you have a very high current, that is IP, and very low current, that is IB. So if you try to calculate the mean current, so the magnitude of mean current is let me take it, the value. So the if you try to calculate the mean current, so which is given by I mean, so that is nothing but IP into TP plus IB into TB by total time duration, that is TP plus TB, right? So this is the magnitude of mean current. So if you see the mean current value, it will approximately lie at this level. But in our normal conventional welding process, where we are using let's say a constant current waveform, so there the mean the current value will be approximately like here. So this is the mean current for conventional one or constant current waveform, constant current waveform, and this is a mean current, I mean, for our pulse waveform. So this is a I mean for pulse one. So you can see the I mean, just by using such waveform or pulse, we have got a drastic decrease in the mean current from here to here, simply with the same like results, like to achieve a spray mode. Here also we are going to achieve a spray mode, but with the very low I mean value compared to the conventional one. So by supplying a low I mean itself, you are getting the spray mode in case of GMAW. So the advantage of getting a spray mode at a lower current itself, so is what? So by doing so, what will happen? Your heat input, since you are supplying a lower I mean current, so the heat input is going to decrease. Means you are putting a lesser amount of heat inside your material to be welded. So obviously, if your heat input is less, then you are causing a less damage to your material in that case. Similarly, here also we are going to get the spray mode. So this is these are the very big advantage that we will be achieving using a pulse type of GMAW process. Now, coming to the problem, so in pulse GMAW, as I told, the mean current is going to decrease, right? So here you can see the mean current is this one, and the conventional process has mean current this one. So mean current is going to decrease. It's not going to increase. So this, what you said, Mohan, is not correct. Mean current is going to decrease basically. And then drop transfer is promoted. Yeah, that's true. Heat input is going to increase, which is not correct. Heat input is basically going to decrease because the mean current is decreasing. I mean is going to decrease. Then in that case, the heat input is also going to decrease. And then jetting spray occur. So since the mean current itself is lower, then there is no chance of jetting spray. Normal spray will be happening. So all these options are wrong. Only option A, which is saying drop transfer is promoted, is true. I hope it is clear, Mohan.
Yes, sir.
Yeah. Now we'll move to next question. Which mode of laser beam welding is preferred to achieve increased depth of penetration? You can read the options and tell your answer. Connection, bead on plate, keyhole, or overlap. So it's very simple. I've already told. Yeah. So that's right. So basically there are two modes. We'll try to see here. Okay. I suggest you solve this problem number 6 also, and then we'll try to understand the concept behind keyhole and conduction. So your answer is right, that is keyhole. Try to solve this problem number 6 also, and then we'll see what is keyhole, what is conduction. Thin section automotive grade steels are laser beam welded in conduction, bead on plate, keyhole, or pilot. So in the first case, problem number 5, you want depth of penetration to be high. So obviously you are using a thicker sheet to be welded, like this. Then only you want to penetrate it so that it can join. But in second case, let's say it's a very thin sheet like this, and now you want to join them. So in that case, what mode you will be preferring? Keyhole or conduction, bead on plate or pilot mode? Yeah, true. So it's nothing but conduction mode. Now we'll one by one see what is basically keyhole and conduction mode. Both of your answer is correct. So if you see the difference between conduction mode and the keyhole mode, you can see here on my screen. So coming to the power, because the power density is also is the main thing which is going to govern how much penetration you are going to have inside your material. So the power density is in keyhole mode, it is less than. So this is how this conduction mode looks like. So here you can see just below the surface, certain depth, very less depth from the surface we are going to penetrate. But here in the keyhole mode, almost we have penetrated the entire thickness. So this is how keyhole will look like. The shape, the name of this keyhole mode is coming from the shape of this hole, which looks like a keyhole in our door key, gate key. So this is how the shape looks like. So the name is keyhole. So the power here is less than this, and here power is much more than 10 to the power 6 watt per centimeter square. Coming to the this heating the workpiece above the melting temperature without vaporizing. So here we are avoiding the vaporization. So we are not going to form a vapor, and that vapor is going to contribute in forming this keyhole. So we are just melting, and that melting is up to certain depth from the surface. The penetration is controlled by the conduction only. So here the penetration is through conduction mode. Coming to the keyhole, the molten metal start vaporizing. So since the power is very high, so it will absorb the laser and it will start vaporizing. The metal will start vaporizing. So the vapor pressure will be coming into picture. Now opens up a blind hole or keyhole in the molten metal. So it will lead to open a keyhole here. Now vapor pressure from the hot metal keeps the hole open during the welding. So if you are welding here, that hole will be kept open, and increase the energy efficiency of welding process due to multiple reflections of beam within the cavity. So since the laser is going inside the cavity, so the reflection from the wall or the cavity will be happening, and that will basically minimize the laser beam loss. So the beam is because different metal have a different absorptivity. So let's say it is absorbing 30%, then 70% is reflected back. But if you are doing in a keyhole mode, that reflected beam will be falling onto the wall itself. So it will be again contained. So that that will ultimately lead you to increase in the energy efficiency. So this is how this keyhole and conduction mode will look like and have a different features. So you can see here it is just below the surface, the penetration has happened, and the keyhole mode, it has almost penetrated through up to here. So you can see the features. So I hope it is clear, keyhole and conduction. So here you can see conduction mode is normally used for welding foils, thin sheets, whereas keyhole mode is used for much thicker section. So this is a thicker section which we want to weld. So we use the keyhole mode. Here it is thin section. So conduction mode is enough to give you good weld. So Mohan, it is clear, the keyhole and conduction mode of welding in laser beam welding.
Yes, sir.
Yeah. So now you have already given the right answer. So for a thick section, we'll go for keyhole, and for thin section, it's conduction mode. Good. Now try to read this question and tell your answer. The shape of weld pool in laser beam welding is generally. So it's a circular or teardrop like this, or teardrop will be looking like this, or an elliptical one, or a square. So if you are doing a laser welding, let's say this is a high energy laser beam falling onto your base plate, so what will be the shape of weld pool? Circular, teardrop, or elliptical, or square? Yeah, so as you said rightly, the shape of molten pool will be teardrop, like this in case of laser beam welding. Correct. Since you are having a very high beam, energy beam process, plus it allows you to move very fast, so the weld pool shape will be automatically coming into the teardrop. This is coming from the speed. You are moving from left to right, so the weld pool will be moving like this. So for a certain time it will be like this, after some time it will be like this, and so on. It will keep on moving, and the metal left side will be solidifying and the right side will be melting. Coming to the next problem, try to read and answer. Recoil pressure in keyhole of laser beam welding is due to. So we have seen all the forces involved in laser beam welding. So I also told you from the for the recoil pressure that responsible thing is vaporization of melt. So metal is vaporizing from bottom to top, and this movement of vapor from bottom to top will generate a recoil pressure in this direction. So it's a kind of thrust which is generated due to escape of the vapors. So the vaporization of metal is the right answer. Yeah, correct. Coming to the next problem. Preset gap during laser welding of galvanized sheets or steels in overlap configuration is required. Why it is required? To overcome the gravity, to overcome the surface tension, release vapor pressure, improve plasma drag. So I told you that if you have a galvanized sheets which you are going to weld, so let's say it is galvanized, that is zinc coated sheets or steel. So in that case, a zinc vapor will be easily forming. So you have to allow those vapors to escape. Otherwise, it will, if it gets trapped, then it will generate the defect inside the weld. So what we do is we maintain in the overlap configuration, we give some preset gap like this. So this preset gap will allow the to escape the vapors of zinc, so that it won't get trapped. So for this, the right answer will be release of vapor pressure. So in order to release the vapor pressure, we have to give certain gap between these plates so that we get a good weld. Is it clear, Mohan?
Yes, sir.
Yeah. Now we'll solve this next problem. When consumable wire diameter increases, melting rate of consumable in GMW will increase, decrease, do not change, or increase exponentially. So you are, let's say this is our diameter D. So if your diameter is increasing, so you are going to increase the diameter, then the melting rate, this MR, is going to what? You say decrease. So before answering, let's see what is the relation between wire diameter and the melting rate. So let's say melting rate is denoted by M, then this M is given by a constant A times current, welding current, plus and another constant B times L current square upon pi R square. So M is what? Melting rate. You can make a note of it. Melting rate. I is what? Welding current. L is what? Stick out length. And R is what? Wire radius. So the filler wire radius. Right. So as you can see in the relation itself, the melting rate is inversely proportional to the square of the wire filler wire radius. Yeah. So if you increase the wire diameter, what it's going to do is it will decrease the melting rate. So melting rate of consumable in GMW is going to decrease. So the right answer is option A itself. So you got it right. So what is stick out length? Do you know? Mohan?
Sir?
What is meant by stick out length in this formula? The L is there, na? So what
Yes,
we call it as a stick out length. So are you aware of this stick out length?
So, sir, the consumable electrodes length, I think.
It's not the total entire length. So let's say this your welding nozzle from where you are passing the filler wire, right? And here it is the base metal. So this we call it as a contact tube. So it's made up of ceramic, and for different welding process the design will be different. And this is what the filler wire is coming out from this tip. So from this base metal and to the tip, this distance we call contact tube to base metal distance. This distance we call it as a contact tube to base metal distance. And this distance from contact tube to till where the filler wire is coming out, we call it as a stick out length, and it is denoted by L. So this much length only we call it as a stick out length. Is it clear? Hello? Your voice is not coming?
Yes, sir.
Yeah. So if it is a numerical problem where they have shown both the lengths, this much length and this much length, and you have to put the value of L, so you have to choose this length only in case of L, right? So this L is nothing but from here to here distance. So we call it basically CTWP, not CTBM, contact tube to workpiece distance. So this is our workpiece and this is contact tube. So this distance is called CTWP, and this is stick out length. So yeah, we'll move to next question. A few more questions. When stick out length increase on the same formula, when stick out length increase, melting rate of consumable in GMW will what? Very simple. Just now we saw. Yeah. So here it is. Here itself, M is directly proportional to L. So as the L increases, M will also increase. So it will increase. Correct. This problem, droplet detachment in consumable electrode welding is always promoted by So it is related to the force balance in metal transfer, the consumable welding processes. So what do you think? Droplet detachment in consumable electrode welding always from. So let's say this is our consumable and then this is a droplet. So try to read it very carefully. Always promoted by. So I have given you the case, especially for gravity. So what if, like here, you want to transfer the droplet from this place to this place, like at the bottom. What if you are doing uphand welding like this, and you are going to weld this sheet, and here you are going to make a weld. So in that case, you want to transfer the droplet from here to here, but the gravity is acting in this way. So here, can you say that gravity is assisting or promoting? Here you can say it is promoting. It is helping this droplet to fall down. But here, can you say it is promoting? What?
No, sir.
So here it is against. So gravity is in this direction and you want to transfer in this direction. So it is not promoting. So we cannot say that gravity is always promoting. So this is not the correct. What about surface tension? It will
resist.
So this is also not correct. Vapor jet forces
Also will resist.
So only thing is plasma jet forces, which is trying to detach this bubble. So the right answer is option B. I hope it is clear. So 2 more questions for today's session and then we'll wind up. In cold metal transfer welding, primary metal transfer mode is. So we also call it as a CMT, cold metal transfer welding process. Primary metal transfer mode is short circuiting, globular, drop transfer, jetting spray. So I will correct. Short circuiting. We'll see the how the things happen in CMT process. So here we have a consumable electrode and we are passing some amount of current through it. So let's say we are supplying 120 ampere of current. So as this filler come closer to your workpiece, so what will happen? That voltage. So you can see the voltage is given by the rounded circle. So as you are coming closer to the workpiece, the voltage is going to decrease. But what we are doing is, when we are just touching the base plate and the electrode, we are making current also almost zero or very low, very low. So let's say here it is 120 ampere, here also let's say 120 ampere, but the moment it touches the base plate, we are making it very low. Let's say we can call it 30 ampere. So what will happen? The molten droplet will form and now we will retract. We are bringing it closer and now we are taking it out. So what will happen? During removal of this filler electrode, we will slightly increase the current, let's say 30 ampere. So you can see here the current graph, we are making it to very low, but again slowly we are increasing the current while retracting. So here the process of bringing the electrode closer to workpiece, and now this process is while removing the filler from the workpiece. So we'll slightly increase the current. So what will happen? By increasing the current at the neck, this is the neck which is forming, metal droplet neck. So the resistance of this neck will be giving this joule heating, that is I square RT, So due to this resistance heating at the neck, this droplet will be making a globule like this, and it will get detached, and then again will go back to normal position like here. So this is how the metal droplet gets transferred. So initially we have a very high current, but the moment we touch, we make the current very low, and then again slowly we increase the current so that the droplet get detached by pinching action, or you can see the resistance heating at the neck of the droplet, and then while retracting, this droplet get detached and it get deposited here, you can see. So this is how we have this metal transfer during CMT. So here you can see, as it is touching the workpiece, and during this only metal transfer is happening. So basically here short circuiting is happening, that is your filler is touching your base material. So the primary metal transfer mode is short circuiting. So you got it right. The last problem of this session is in pulse GMW, TB is, what is TB? I have already explained. Background time, background current, peak time, average current. Very simple. Please mark your answer. Yeah. It's not peak time, it is TB. B means background. There was another term TP. Here it is asking about TB. So if you go back to the slide where I have explained it here. So TP is for peak current, maximum current, TP. But for a minimum current, we call it as a TB. And also we call it as a background current. So background current is TB. B for background. Yeah. Background time. Sorry. So it's not the peak time, it's the background time. So the right answer is TB is nothing but background time. So yeah, thank you so much for joining this live session for solving some example problem. If you have any doubt, you can ask, or else we can end this session here itself. Yes, Mohan. Do you have any doubt?
No, sir.
Yeah. So okay. Thank you so much for joining this live session. I hope you have learned something from this, and then go back and then try to solve the assignment problem. That is the third assignment, and try to have a maximize your score as much as you can. So yeah. Good. So we close this session. Thank you so much once again. Good night.
Thank you, sir. Thank you.